Real-time identification of robot payload using a multirate Quaternion-Based Kalman filter and recursive total least squares is a joint work of the University of Ferrara and the University of Modena and Reggio Emilia in Italy. The paper addressed the problem of estimating online the inertial parameters of the payload mounted on the end-effector of an industrial robot. The proposed solution relies on force torque measurements from a 6-axis sensor mounted on the end-effector, the end-effector pose as calculated by the industrial robot controller, available for user programs or external equipments at moderate sampling frequencies, and linear acceleration and angular velocities from inertial sensors sampled at higher frequencies. The estimation scheme relies on the online execution of a two-step procedure. In a first step, a multirate Kalman filter fuses data from the inertial measurement unit and the robot kinematics to estimate the linear acceleration, the angular velocity, and the angular acceleration of the load. Then, the outputs of the multirate Kalman filter and the measurement from the force torque sensor are processed by a recursive total least square algorithm to generate the estimation of inertial parameters. The multirate Kalman filter for sensor fusion has a common prediction model based on the Quaternion exponential formula and a correction model that depends on the data available at a given time step. There are three cases, one in which only the data from the inertial measurement unit are available, one in which only robot kinematics data are available, and one in which both data are available. The experimental setup consists of a Fanuc LR-mate robot whose pose is sampled at 100 Hz, an ATI Mini 45 force torque sensor sampled at 500 Hz, and two alternative inertial measurement units, one sampled at 250 Hz and one sampled at 100 Hz. The payload is a steel block whose inertial parameters are known from geometry. This table describes the average errors on the estimation of the inertial parameters. These results are improved with respect to previous solution, not including sensor fusion. In the future, we will investigate the generation of trajectories that can maximize the estimation accuracy while minimizing the range of motions.